see. All right.
It's 40 minutes. Great. All right, our next speaker is going to be Neil Cornish, who is going to tell us about black holes and pulsar timing arrays.
Thanks, Cole. This is the first talk I've given on pulsar timing arrays. Those of you that know me from the LISA activities, this does not mean that I've given up on LISA. I've just decided to also look at pulsar timing arrays. So this is the picture in the background here. It's an artist's conception of the square kilometre array which they've plonked down somewhere in Australia. And it's once we have radio telescopes like the SKA that pulsar timing will really become a powerful tool for doing gravitational wave astronomy, but we might get to detections before we have the square kilometre array. So for those of you who've not heard many talks before on pulsar timing detections of gravitational waves, I'm actually going to start with some very basic derivations of the timing residuals and things like that. So this is going to be a first principle. It's going to start at first principles just for those of you that haven't seen it before. This is a graphic that I think is shown in every pulsar timing talk of the concept that using the pulsars as very accurate natural clocks and seeing changes in the arrival times caused by intervening gravitational waves. So that's the general idea. These arrays of pulsars here, there's only, I think, 6 shown, will be probably, of order many tens to hundreds in the next decade. So this large array of pulsars being used. And pulsar timing is actually it's somewhat unusual if you're used to especially LIGO or even LISA, where most of the sources are transient and moving through. Pulsar timing, if we're looking at signals from supermassive black holes, those supermassive black holes are going to dwell in that band and not move through in our lifetimes. So once you've made your detections of black hole systems with pulsar timing, that's all we're ever going to see for the rest of the time that in our lifetimes that we ever observe. So it's very much like in astronomy or just naked eye viewing of the bright stars around us. They're the same stars that our ancestors saw. We get sort of one realization of the gravitational wave sky in the pulsar timing band. So we'll see these sources, and we'll probably give them, we should give them individual names, not just zip codes, because there's only going to be a few of them, maybe order of half dozen or a dozen eventually in our lifetimes that we'll actually be able to detect. So I think we should give them nice names. So the outline of my talk is I'm going to go through a derivation of the response function, and then I'm going to talk about, and this will make more sense once I've actually gone through that derivation, the so-called pulsar term in the response function. I'll talk a little bit about detecting stochastic backgrounds with pulsar timing arrays, and in particular backgrounds from the combination of signals from many different black holes. But the main thing I'll talk about is what we can learn about individual sources using pulsar timing. So what kind of resolution would we get in terms of where the sources are in the sky, and also on their distances and masses. And I'll also talk a little bit about the prospects of using pulsar timing as a way of testing general relativity. Okay, so the measurement, the data in pulsar timing are these time of arrival of the pulses from the pulsar, and there's an electromagnetic contribution and a gravitational wave contribution to these arrival delays. So the pulsar's ticking at this fairly regular rate, but we see the pulses arriving at a somewhat irregular rate because of various effects, including potentially gravitational waves, but also noise, scintillation effects of the radio waves passing through matter in the universe. So in modeling the electromagnetic signals that you see, you have complications that come from the pulsar period changing. So you've got the first and second derivatives of the pulsar period from the spin down. But there's also can be glitches. The time of arrival, actually, it depends on the where the pulsar is in the sky, just because of the movement of the Earth around the Sun. So you've got the ephemeris there encoded in changing the. So you have to take all of that out. At a higher order effect, you actually get timing parallax from which allows you to infer the distance to the pulsars from the arrival time of the pulsars. So you have all this electromagnetic information that you have to take into account in getting to your pulsar residuals, and then also the gravitational wave signal on top of that. The way the analysis is done right now is this term, the electromagnetic contribution to the timing residuals, is modeled first, and then they go after the gravitational wave signal after making all of these subtractions and fitting for all these things. Ultimately, that's a dangerous thing to do because you can fit out some of your gravitational wave signal while fitting for these terms. And so the way forward in the future will be to do this kind of analysis simultaneously or iteratively, so that you don't go modeling out part of your gravitational wave signal in the fitting that you have to do to for the electromagnetic contributions. The gravitational wave contribution you can derive very much like you do the calculations for LIGO or LISA. A one-arm interferometer here, A hat is the direction to the pulsar from the Earth, L is the distance to the pulsar, and you've got to integrate the gravitational wave strain along this line of sight to the pulsar. And one of my equations didn't, there it is. So here, if we have, say, a black hole system in the n hat direction, some distance d away, and you've got the pulsar in the a hat direction, some distance l away, and mu being the angle between the line of sight to the pulsar and the line of sight to the black hole, then k hat then is the propagation direction of the gravitational wave. And you can get in situations with, usually we would just set k hat equal to minus n hat, because for LIGO and LISA, the distance to the sources, d, is very much larger than the length of the detector, so you usually don't worry about any deviations from this being a plane wave. But in pulsar timing, as Sam Finn and one of his students, Deng, showed, you do need to worry about the corrections from this being a plane wave. So you actually get, this is the first correction from the plane wave approximation in terms of the propagation vector. If you compute this contraction of the arms, the pulsar arms here into the gravitational wave strain, you get a factor of sine squared mu then into h plus and h cross. And so this is the sort of polarization response of a one-arm gravitational wave detector. You're used to the more familiar peanut shape that you get for an L-shaped interferometer, but this is the antenna pattern for an individual pulsar. So if we then go ahead and do this integral, oh no, sorry, wrong slide. Just a more general comment here. In terms of comparisons between LIGO, LISA, and pulsar timing, in terms of the response, the formula that I wrote down is actually valid for all three. when you're working with LIGO, there's this quantity, the transfer frequency, which is when the product of the angular frequency of the gravitational wave times the length of the detector arm equals 1. And basically that's sort of setting the scale at which the gravitational wave's wavelength sort of is on the scale of the detector. So for LIGO, with a 4 kilometer arm, that would give you 10 to the 4 hertz for this transfer frequency. For LISA Classic, you get 10 to the minus 2 hertz. For pulsar timing, you get 10 to the minus 12 hertz. And when you look at the frequencies in which these different detectors are operating, LIGO is always operating in the long wavelength limit, except maybe a little bit at the very highest frequencies it starts to touch in on and having to worry about finite arm length effects. LISA sort of operates in a mixed regime where for the lower frequency sources it can be treated in long wavelength approximation, but then the finite arm length effects start to kick in as you go past 10 to the minus 2 hertz. For classic LISA, it's higher for the E-LISA configurations. But pulsar timing is always operating in a very different regime. It's always operating in the short wavelength regime, so the complete opposite to LIGO, which actually, when you see those plots of the pulsar sensitivity that look like a tick mark, the line coming down on the left is just set by your observation time. The minimum frequency you measure is 1 over your observation time, but that tick going up is this drop-off because you basically, the waves are cancelling inside the arm. So that's just the general flavour. If you've worked on LIGO and LISA, just putting in perspective how pulsar timing response is. It's kind of like the very high frequency LISA response function. Okay, so doing this integral along this path, you get 2 terms. You get the Earth term, which is the antiderivative of the gravitational wave strain at the instant that the gravitational wave is hitting the Earth. But then you have the so-called pulsar term, which is the antiderivative of the gravitational wave at the time that the gravitational wave encountered the pulsar, okay, so sometime in the past. And here we have this correction. And so you put all that together and you get your final expression for the response in the time domain of a pulsar, a single pulsar, and you end up with a 1 plus cosine mu dependence, which is, again, that's the angle between the line of sight to the pulsar and the line of sight to the black hole. So this pulsar term is traditionally ignored because the what is usually looked at is cross-correlating the signals from different pulsars to look for an overall stochastic background. And when you do that cross-correlation for isotropic Gaussian stochastic background, the pulsar terms cancel out and only the Earth terms add up coherently. But the pulsar term is important if you're actually wanting to look at individual sources. It gives you the potential to actually improve the measurement of the pulsar distances, the potential to improve the sky localization of the source, and it's essential if you actually want to find the mass and distance to the source. So if you ignore this term, you will not know the mass and distance. So you'll just know that you've got a gravitational wave signal with some amplitude, but astrophysically, it's not particularly useful information because if you can't say, you know, what kind of system did you just measure, what's its mass, or where it is, it's just not very useful for doing astrophysics. So in the last year or so, there have been 3 papers that I know of at least that have discussed using this pulsar, the so-called pulsar term. The paper I already mentioned by Deng and Finn, one with Vincent Corbin and myself, and then this other paper here with Li et al. And I'm going to talk a little bit about those 3 papers today and contrast their findings. So I'm going to be talking about using pulsar timing in the context of looking at black hole signals. I'll just be considering quasi-circular black holes, so ignoring any eccentricity. And for pulsar timing, you really only need to work to very lowest post-Newtonian order because you're not really seeing a very strong chirp. So you've got the usual H plus and H cross, or at least the antiderivative of them. And they're slowly evolving. So if you actually look at the chirp time, which is omega divided by omega dot, I don't think you can actually read any of these equations, so that's why I have to kind of tell you what every term is. You get something of order 10 to the 5 years if you scale it by the characteristic frequencies and masses that we're looking at. So the chirp time, this is what I was saying about, whatever sky we see with a pulsar timing array, it'll be the same pulsar sky that our grandchildren will see, right? This is sort of a one-shot view of that part of the gravitational wave spectrum. It also means that if you have a observation time of, say, 10 years or so, is sort of a reasonable time to imagine doing these observations, maybe, decades, you won't actually be able to measure the chirp typically for the change in frequency that you see at the Earth over that 10, 20-year span is not detectable. But to be able to actually, the minimum detectable chirp mass is around 10 to the 8 solar masses, then scaled by an SNR of 10 to a power 3/5. But the observation time in units of 1,000 years, and of course you're not going to wait for 1,000 years to do these observations, but you've naturally, if you include the pulsar term, you naturally build in 1,000-year observation timescales because the pulsars saw the gravitational wave thousands of years ago. So when you include the pulsar term, you do get an effective observation time that's thousands of years. So you can measure the chirp when you include the pulsar term. Okay, so you have the phase of the gravitational wave at the Earth, which is some overall constant phase plus omega naught times t. Then you have the pulsar phase, which is some overall phase plus the frequency as seen at the pulsar times t. That's given, you can, since these are slowly evolving, you can relate it to the omega dot and the omega, so this brings in the chirp mass here. So the pulsar orbital frequency is one thing that we can look at, the measuring, the angular frequency of the gravitational wave seen at the pulsar, but you also have this phase term, which depends on the same initial phase, then plus a term that goes as the distance, the projected distance to the pulsar times the angular frequency, and you can also go for this spherical wavefront correction. And while this factor of L over D is very small because L is of order, kiloparsecs, and the distance to the black holes are going to be hundreds of megaparsecs, when you actually multiply that by the frequency, this actually can cause order, fractions of a radian change in the phase. So you do get this parallax type, effect from the spherical wavefront corrections that you need to take into account if you want to use your pulsar term in a coherent analysis, at least for relatively nearby sources. Now, what does this pulsar term do? You've got the you've got the Earth term with the Earth phase and the pulsar term with the pulsar phase. The amplitudes are basically pretty comparable, so just using a trig identity, you get the average phase, and then you get an overall slow beat envelope. So the detected timing residual from a single black hole puts this kind of structure in that you can get like a beat envelope from the interference between the pulsar term and the Earth term. And the structure of this beat envelope actually encodes the information about the mass and other things. So one of the interesting things, I just had that little thing pop up, you can get both constructive and destructive interference. So for example, if I took an array of 40 pulsars and I look at the SNR in each individual pulsar as a function of the angle between the line of sight to the pulsar and the line of sight to the black hole, if we only looked at the pulsar term, if we only looked at the Earth term and ignored the pulsar term, there would be a monotonic increase in the SNR as the angle went from, cosine of the angle goes from -1 to 1. But when you include the pulsar term, you can get both constructive and destructive interference, so that the signal to noise does not increase monotonically with the cosine of the angle. So that actually is quite important for some things that come later. So,
what about the bottom?
Sorry?
You had two graphs.
Oh yeah, sorry. They were just different chirp. These were different chirp times. This was a more slowly evolving system and a faster evolving system. The slower evolving systems have greater interference because the two frequencies basically match. The more rapidly evolving ones, the cancellation's not as precise since they're different frequencies. So you see a much bigger fluctuation when you have slowly evolving systems than more rapidly evolving ones. So as I mentioned, there was these three papers that have looked at the pulsar term. Two of the papers focused on the effect of this phase correction, whereas Vincent and I focused more, we had both terms in, but we focused more on the effects of the different frequency that you had at the pulsar. Now, if you just go through a standard Fisher matrix analysis, the uncertainty in the phase of an individual pulsar can be measured to 1 over the SNR of that signal. That then, when you look at the back of the expression for what how that pulsar phase depends on the distance and the sky location, that suggests that by including the pulsar term, you would get measurements of the pulsar distance to parts in 10 to the minus 3, so the pulsar distances of order kiloparsecs. So this would suggest that including the pulsar term will give you parsec-type level measurements of the distance to the pulsars. And it also suggests that you'll get arc-minute angular resolution. Okay? Now, if you use the frequency evolution, if you're looking at the pulsar frequencies, then again from a Fisher matrix analysis, the log of a frequency is measured to 1 over the signal to noise, but that then translates into measuring distances to pulsars to order 30% and being able to measure angles on the sky to 50 square degrees. So there's quite a discrepancy between what you would expect to see if you use the phase information or the frequency information. So that's something I'm going to come back to shortly. Okay, so the big hope for pulsar timing gravitational wave astronomy is to detect this binary black hole background from supermassive black holes. These are figures taken from this paper, Sassana, Vecchio, and Volontieri, and looking at a couple of different realizations of possible models for the distribution of these systems in the universe as a function of redshift and mass, and then looking at actual realizations then of the backgrounds in characteristic strain that you would get from these different populations. And one of the things that you then would want to do for trying to detect these is you would take the timing residual in two pulsars here labeled I and J and calculate the cross-correlation of those timing residuals. And Hellings and Down showed that this cross-correlation for a stochastic background would have a characteristic dependence on the angle theta between the two pulsars. So this really, I could have labeled it theta sub ij, so it's the angle between the ith and jth pulsar, should have this characteristic dependence on the angle between the pulsars, and then the overall factor there depends on, an integral over the gravitational wave energy for the sort of strength of this signal. But this correlation factor, this is the theoretical curve here, the Hellings and Downs curve, showing how it varies with angular separation in degrees. And this is just simulated pulsar data with, noise in the measurement due to scintillation and other effects. So this is the kind of thing that people are hoping to do with pulsar timing is see as a function of the angular separation between the pulsars, do they see evidence for this characteristic curve? And there's a classic paper by Hellings and Downs where this was first put forward as a technique, and then others where it's been looked at in different frequentist and Bayesian implementations of this idea. So one of the things, though, when you actually go in and look at these realizations of these black hole backgrounds, they are rather jagged. They show, a lot of structure. They don't look particularly like a uniform stochastic background. And the finding from Sassano, Vecchio, and Pellicino's paper in 2008 is that above 10 to the minus 8 hertz, you're actually, this background is really coming from relatively few massive black holes in the nearby universe. So rather than this being a background made up of millions of weak signals, which really would look like a stochastic background, this is a sort of a confusion noise made up of tens or hundreds of signals dominating this signal. So it really isn't a particularly Gaussian stochastic isotropic background at all, which is what Hellings and Downs' derivation was for. It was not actually for using pulsar timing to detect black holes. People have just assumed that, that you've got this black hole background, so we'll treat it like a stochastic background and use the Hellings and Downs result. Well, it isn't a stochastic background, and I've started working with Sassano on Alberto on this, is that you don't get the classic Hellings and Downs curve when you only have a finite number of sources. And what's more, the pulsar term, which averages to 0 in the limit of an infinite number of sources, does not average to 0 and adds significant noise onto the curve. So just to illustrate this is the correlation function between two pulsars as a function of the angle between the pulsars. So this is like the Hellings and Downs curve now, but rather for a isotropic background, this is just for two individual black holes. So black hole 1 is in red, black hole 2 is in blue, and those two black holes happen to be at different sky locations, okay? And you see that they produce different correlation curves. Now, if you add up an infinite number of these spread uniformly across the sky, the sum of all of these different correlation curves gives you the Hellings and Downs curve. But when you're actually dealing with a background that only has it's dominated by tens or hundreds, the curve you get just depends on that realization, and it's not the Hellings and Downs curve. So the analysis technique that is being touted for how to go after detecting this, at least, we haven't finished doing the calculation yet, but I don't think it works. So we'll see. I'm pretty confident it doesn't work, but I could be wrong. I'll know by the end of the week, or end of next week, because I won't get any work done this week, but end of next week, I'll know the answer. But I'm pretty sure it doesn't, based on this. Okay, so back to considering individual sources and the importance of using the pulsar term. So when you look at how the phase of the pulsar term depends on the distance of the pulsar, I've got that if I change the distance of the pulsar by order 1 parsec, I get an order pi change in the phase, okay? So that suggests that to match the pulsar phase correctly, I have to know the distance to the pulsar to of order a parsec accuracy, okay? Or vice versa, I could use the gravitational wave signal to then be able to determine the distance to the pulsar to something like that level. in the paper that Sam wrote, what they were looking at there was in the era where we have the kind of accuracy and the timing residuals that we need to see these systems, the timing parallax in the pulsar arrival times will give you the distance to the pulsars to of order parsecs just from the parallax. Okay, so we'll actually already know from the electromagnetic signal we'll have an error bar on the distance to the pulsars that's going to be of order parsecs. It's better for the nearby ones, worse for the more distant pulsars. So if you take that in as being like a prior information on the distance, then and say, okay, let's pretend that we know the pulsar distance now, and look at what happens as we change the angle between the pulsar and the black hole. So this is sort of like then a measure of the sky location. That actually gives you, and you can't read this at all, this is taken from Sam's paper, that actually gives you...
That's not the reason you can't read it.
But if you, that's of order 5 or so arc minutes across here. I mean these ticks here are 5 arc minutes across. Okay, so you get this very precise sky localization. Okay, and that's true, but there's a bit of a complication. And here is from a this is some output from Markov chain Monte Carlo study that Vincent and I did. And here we were using a prior on the pulsar distance, which was of order a parsec, okay, just to put us into that era where we'll have those kind of distances. And what I've got plotted against each other are the output from the Markov chains of the distance measured to pulsar I, so this is maybe pulsar 20 in the array and against pulsar, say, 7 or something like that. And you see that there's this incredible multimodal structure. And basically what it is, it's the winding, because you get that phase only modulo 2 pi, so there's multiple solutions, right? So you just wind around. And in fact, for this particular simulation, there are 5 by 10 to the 20 modes to the posterior, okay? And it took quite a Markov chain to hop around between those. This is actually, what I'm showing you here is where I held the distance to the black hole fixed, the frequency of the Earth term fixed, and the chirp mass fixed, okay? And then you see the structure. If I allow, say, the location on the sky of the black hole of Aerie, which we should, that structure washes out. You don't see the islands anymore because it's got smeared by, well, basically we're now projecting down from a higher dimensional space, and the projection down just onto the, Li, Lj plane no longer shows the modes, but they're still there. It's just they now live in this higher dimensional space, and when you project them down, you just don't see them. In fact, you can actually see them again here if I plot the cosine of the angle between, say, pulsar I and the black hole and the distance. You don't see them if I just plot it like this, but if I zoom in to each of these panels, you can see that these are the multiple modes of the posterior again showing up, okay? And even if you shrink the prior even further to, which would now be sub-parsec resolution, you still get the multiple modes. Here they weren't very well, this simulation was still running when I produced the graph, so it hasn't yet mapped out these modes. They take a while to get around all these different modes of the posterior. But the basic point is that while each individual one of these modes has this incredible, arc minute resolution, there's a shitload of them. And so when you add it all up, it gives you a really crappy angular resolution when you add up across all the modes. So what you get, unfortunately, is nothing like arc minute resolution. You get tens, hundreds of degree resolution at the end of the day because of all these modes. For those of you MCMC aficionados in the audience, you might wonder how we managed to jump between this massively multimodal posterior. And the trick turned out to be, instead of using the pulsar distances as the variable, we actually use the pulsar initial phase as the variable. And those are related to each other by a term that varies here, which is defined modulo 2 pi, which is sort of sub-parsec scale, and then an integer winding number, which, with its winding number being around 1,000, and this is kiloparsec scale. So by using this phase as the variable rather than the pulsar distance directly, that automatically, by changing this integer n, that hops us across the modes. Okay? So that was our mode. The mode hopping is by hopping the winding number to the distance to each pulsar, and that allows us to hop all around this forest of secondary modes. You can actually ask, well, how well can I measure the distance to the pulsar using the just the gravitational wave signal? And if I don't assume any prior on the pulsar distances that we would have from parallax, it turns out the pulsar distances are only measured to of order 30% just from the gravitational wave signal alone. So you don't really constrain the distance to the pulsars very well directly from the gravitational wave signal. And the sky localization, like I said, without the pulsar term, it's of order a couple of hundred square degrees. With the pulsar term, it's of order 100 square degrees. So really, I mean, it's different from different realizations, different SNRs, different sky locations, and whatever. But basically, the pulsar location, I mean, see, the determination of the location of the black holes is pretty bad. So, you know, the prospects for doing looking for counterparts aren't as promising. In fact, in the paper that we have posted on the archive, we quote numbers that are more like tens of square degrees rather than hundreds or even 5 square degrees. It turns out that those numbers are wrong because our original code wasn't exploring all the modes properly, hopping around, and so we're only seeing a subset, and so we were getting only a fraction of the full map. But now that we've found a way to explore all the modes, we've actually found that the sky error is a lot larger than we thought. We were just basically trapped. I mean, trying to make our way through this forest of modes, we underestimated the error. So now we see the true error is actually, you know, you don't really you get about a factor of 2 improvement from using the pulsar term, not a factor of 10 like we said in our paper. So I've got to post a new version in the next week or 2 now, so to correct that. In terms of how well you can measure the mass and distance to the black hole, you get order sort of 30%, I mean, again, it depends on SNR and things, of order and the number of pulsars, of order 30% measurement accuracy on the distance and the mass. So that's useful, I think, for doing gravitational wave astronomy. Okay, I've pretty much run out of time, but just very briefly mention, you know, one of the things that pulsar timing is ideally suited for is trying to measure deviations from general relativity, especially in terms of additional polarization states. In GR, you just have the plus and cross polarizations, but in alternative theories, there are 4 other polarization states that you can have, including 3 that are longitudinal. And the problem, if you want to try and measure these with interferometers, this is showing the antenna patterns for the various polarization states, the familiar plus and cross, but then to these different other modes. And you need at least 6 interferometers to be able to tease out the different contribution from each of these polarization states. So you need 6 different interferometers spread around the world, oriented differently, if you want to actually try and use interferometers to measure polarization. The great thing about pulsar timing is you've got hundreds of arms pointing in all these different directions, and so you're able to measure the polarization directly with those. This was a calculation originally done by Ron Hellings in '79 in the context of spacecraft Doppler tracking, reinvented recently by Lee, Genet, and Price, showing that this the Hellings and Downs curve are different for the different modes, the GR mode, the breathing mode, and the various shear and longitudinal modes actually produce different correlation curves. And so that was suggested as a way that we could test GR by looking at how it affects these correlations. And similarly, if you have a graviton mass, it makes changes to the correlation curves. I mean, if our suspicions are correct about the noise essentially that you get, the realization, the cosmic variance in the Hellings and Downs curve from a finite number of black hole systems, none of these tests will be possible because it'll be washed out by that cosmic variance. But if we're wrong, maybe you could do this. So just finish here. I would say that pulsar timing arrays will probably make a detection in the next 10 to 15 years. It doesn't look like the classic correlation analysis will be sufficient, but I'm sure we can come up with a way of doing it. And I think the techniques will actually be a little bit more like some of those that we use in LISA data analysis, where we deal with the individual sources and also include the pulsar term. All right, thank you.
Questions?
Satya?
Okay.